Okay, let's get started. So we're going to be talking about trees today. Trees are a pretty fundamental data structure when it comes to computer science. I'd say next to lists, they're the pretty much most important one, okay? And what we're going to find is that a lot of data structures look like trees, so we can generalize this idea of trees in SML to being able to do any kind of data type, all right? To recap what we did last time we learned about structural induction on lists. We learned that if we want to prove things about the natural numbers, we have to be able to prove things by using the mathematical induction principle, right? The principle of mathematical induction. But for lists in SML, we can still maintain that ability to do induction by doing a different kind of induction called structural induction. And we're going to keep that theme going later on today when we find out that we can do the same thing on trees. Last lecture, we also learned about this idea of tail recursion, which lets us make code more efficient at very little cost to the readability because of this idea of using an accumulator and making tail calls which don't have to do any work after the recursive call. That won't come into play today, but we will talk about that later. Okay. Okay, so this is our schedule for today. We're talking about trees, traversals on those trees. We're going to do a proof, and then we'll talk about how we can generalize this idea of trees to other data types. Okay, and I will define for you what that means later on. Okay, so to talk about trees, I already said that trees are pretty much the most fundamental data structure other than lists, but you might be familiar with this idea of a binary tree, right? And a binary tree just looks like this. It's a node at the top and then two nodes at the sides, and then we store some kind of data at the nodes, right? If you take a 112 or 122, you should be familiar with this concept. But a binary tree might look something like that. It might be a little bit more complicated. We call it a binary tree because a binary tree has at most two children. It doesn't need to have two children always because we see that the 3 node here has one child. Okay. SML doesn't have an inbuilt tree type, but that's fine because it turns out that we can just define it for ourselves. So to do this, we're going to use something called a data type declaration. And it looks something like this. So we write the keyword data type. This is a keyword, so you can't use this as a variable name or anything. Then we say tree is the name of our type equals, and now we're going to say what the constructors are. Okay. So I'm going to write this, and I'll explain to you what it means in a second. But we're going to write empty or node of tree star int star tree. All right. And the basic idea here is what this means is it is a type that is two things. It is two things. One of the things. Can actually get a different color here. One of the things is empty. It's called a constant constructor. It's a constructor for the tree data type that takes in no arguments. So we might say that empty as is itself a value and it's of type tree. Okay. And then we also have node, where node takes in an argument. It is not a constant constructor. It has an argument. So it takes in a value of type. And there's implicit parens here, but you don't need to put parens around it. It takes in a value of type tree star int star tree. Okay. And then you might be able to guess, you might be able to guess what it returns because node is a constructor of the tree data type. So I told you what it takes in. What does it produce? Well, it just produces a value of the tree data type. I'm saying data type here and type interchangeably. Data type is really just declaring a new type. There's not really a difference between like a data type and a type. Okay, it's just that how we declare it looks different. Okay, so this is the type of trees. All right, it is empty or node and no more. And what I mean by that is in the same sense that we had lists, and lists were nil or cons, and you can also say that nil was of type, let's say int list. Okay, it could be any type of list, but let's say int list, and then cons was of type int star int list to int list. In the same way that you might say this, right? We see the correspondence here between these constructors, between nil and empty, which are the base cases, which are the constant constructors, and node and cons, which are the recursive constructors. We see that actually this is a consequence of the fact that data type is a recursive type. We mentioned tree once here in the base case, but we make trees out of other trees the same way that we make lists out of other lists. Okay, so it shouldn't be necessarily an unfamiliar concept because we're using just a simple recursive definition to be able to declare this type. Okay, So moving on, I mentioned about these constructors. This no more idea is going to be really important, okay? We're kind of keeping this going because what this declaration says is that, I have these types, but another thing to say, actually, I guess I had nothing else to say about that. But yeah, it has two constructors, and in particular, that means that we can case upon a tree using cases, right? So I say case T of, where T is a value bound to a tree, and then I would say empty, let's say, goes to 0, or node of LXR, which is how we typically denote this, goes to X, which is of type int, right? Because it's here actually, it's of type int. So this will type check, but this whole expression is able to be written because of the fact that our constructors are empty in node and no more. We get our pattern matching principles still. Okay, so we get to create trees and we get to destruct trees. Remember what I said about destructing data. Okay, let's move on. So let's look at some trees and how we can picture them in our brains. But we have the empty tree, which has no picture because it doesn't exist. It's empty. We have the singleton tree where the root is just the value 150, and that looks like a node that has no children. Okay. If you want to, so at this point, I should say something about how this syntax can start to get pretty verbose, especially if you're writing it in line, because of the fact that these two empties here can be gigantic trees in their own right, which means that if you try to do this, try to write like a big tree, especially on one line, it's going to explode and it's going to like have a bunch of parentheses and you might get it wrong. So if you're having trouble with that, you can use this excellent SML tree converter made by a previous TA, Sue Lee. Basically, you put the depth of the tree in, and then you can like specify some values like 1, 2, 3, 4. You can generate the SML text, and this is now the SML text for the tree that we're describing here, the one that looks like this. Okay, so that's kind of useful for if you want to like generate for any test cases or anything like that. Okay, but yeah, that's kind of a side note. Okay, we can move on to more interesting tree examples. If I wanted to do the tree that's just 1, then 5, and 0, I would have to put a node where my left child, this thing here, is itself a node, right? It's a node of one thing, and we have to kind of put empty like a bunch of times. You note that because there's 4 children that could have existed but didn't, we have 4 empties as a result. Okay, and hopefully that makes sense to you. But you can work through like these typing rules, this rule right here, if it doesn't make sense to you as to why this should type check. Okay. And then on the other hand, if we wanted to do an unbalanced tree, like a non-symmetric tree, 1 and 5, my right, it's the same as the right subtree, but now this node on the right is just empty. Okay, it's empty because there's no tree there. So now I only have 2 nodes. You note that like the number of times that we write node is equal to the number of nodes that there are. That should make sense to you. Okay, but all these are values of type tree. Okay. And the syntax is important to get used to, but it's okay. I already mentioned about how node is a recursive constructor or a non-constant constructor, and empty is our constant constructor, and that they're called a recursive type. Okay, any data type declaration can be a recursive type, but it doesn't have to be. And I'll show you later that the distinction between those two things. Okay. Okay, and I already wrote this case for you, but also we can write one function on trees. So I'm gonna show it to you, and then we'll go through the syntax. Okay. So suppose I wanted to write a function that sums all of the nodes in a tree, right? I'm going to be able to case on 2 things, right? 2 cases, empty and node. In the empty case, the empty tree has no sum. There's no elements in it. So we return 0, right? For the node case, tree sum upon that is now a recursive case. I have to make a recursive call. And in particular, I have to make 2 recursive calls because I have 2 subtrees that I might want to get the sum of. So to do tree sum of node of LXR, you take the recursive leap of faith. If I have the recursive leap of faith, if I assume that tree sum of L is the sum of all the nodes in my left subtree, and tree sum of R is the sum of all the nodes in my right subtree, is it not the case that the sum of the whole tree is those 2 quantities plus my root? Right? So think recursively. It should make sense to you that if I just add up everything on my left and my right, and then I put them all together with the root, I now have everything. So that's exactly what this code is doing. It says, let me sum up the amount of costs, the amount of nodes in my left, add that to X, and then add that to my right. Okay, so it's exactly what I said it would be. Right? It reads like math, or it reads like almost like English. Okay, that's the idea there. All right. But again, note that there are two recursive calls, and we're going to see that there's a tight coupling here with how this affects our proof. Okay. And now I will write this one with you, but we're going to write a function to compute the depth of a tree. Okay. And we're going to define the depth as such. So if I have a tree and it looks like this, so I have like a node here. This is the first depth. So like this is a node of depth of 1, or a tree of depth 1. Now this is a tree of depth 2, and now this is a tree of depth 3. Ignore the data I put in the tree, but the idea is like it's the maximum depth across all paths you could possibly take. And in particular, the empty tree is actually of a depth of 0. I also need to put that. Okay, but that's our specification. Yeah. And the empty tree is like, yeah, it's right up here. And then 0 is above that. Okay, yeah. Cool, so let's do it. So we're going to define this function, but first I'm going to take a little detour and I'm going to give you n, which is an int. Actually, let's say n1 and then n2, which are ints. We're going to define a max function, which takes in 2 ints and then it returns to me their max, right? And we can do this because SML has comparison operators. So we say, if n1 is less than n2, well, then I probably just want the greater of the two, which is n2. Else I want n1, right? Otherwise, if n1 is the same as n2, then I don't really care. Just do whichever, okay? I'm going to define this for you, and then we're going to see what we use it for, okay? Let's define the depth function now, okay? So we're going to do fun, depth, and then we're taking in a tree, right? So let's begin our pattern matching. We're going to say empty is our first case, because when we write a recursive function on trees, our first move is always to write the empty case, okay? And then I'm returning an int. So the depth of the empty tree is, as I said here, 0, because it's it doesn't exist, it doesn't have any nodes. So we'll say 0. And then the depth. Now your next move when you're writing a recursive function is to write node of LXR. Okay. Now this case is going to be equal to, well, I said I wanted the maximum possible depth among all of my children, all the paths to the bottom, right? And it turns out that recursively, we only need to think about 2 paths, okay, if that makes sense. So let me put it this way, right? I define this handy max function for you, and here's the consequence. If I have the maximum depth path on my left subtree and the maximum depth path on my right subtree, or the height of that path, then I just need to pick between them, right? So let's just say max of depth L, comma depth R, right? I'm passing in a tuple of both of these things. Does this look right? Well, actually, I'm just taking the max of these 2 paths. But if you notice, like I've never done any math. I never added 1 anywhere. I have 0. And then this is 0 from like recursively, you can assume like the next case above the base case must be 0. The max of 0 and 0 is always 0. I didn't do any work here. I just straight up like returned the recursive result. So if you're not doing anything with your recursive result, that's a code smell. You should probably think about it because you probably always need to do something with your recursive call. Now, if you're doing a tail call, you might do work before the recursive call, right? But here we're doing like almost no useful work. We're just taking a max. So what I'll tell you is what we need to do, which is to add 1 to it here. Okay, we have to add 1 at our node because when we have this tree or this path, suppose this is of height like 2, and this is of height, well, this is of height 1. Okay, if I take the max of these, the height of my tree is still just 1 plus that. It's 3. So I add 1. Okay. And I won't go into this right now, but I'd like you to check your understanding. Why did I not write like why did I not compare depth of L and depth of R immediately? Like I could have written if depth L is less than depth of R, okay, without using this max function. Why did I not write this? Okay, I'm gonna leave this as an exercise. Okay, but I want you to think about eager evaluation when you answer that question. Okay, all right, let's move on. So we're going to talk about tree traversals, which are a way of getting data out of a tree. So we talked about trees. We talked about being able to do stuff on those trees, but we don't want to, let's say, repeat too much work. And what I mean by that is I can define functions on trees, and trees are a way of storing data, similarly to a list. Actually, trees are like, in a sense, strictly more powerful than lists. So suppose I wanted to write a function. Suppose I wanted to, in particular, write a function to count the number of nodes in a tree. Okay, and I'm going to write this with you real fast, but I'm going to tell you it's not going to be super exciting. Okay, so count. Remember, first move, empty, right? That's the first move when we're writing a function on trees. And then we're going to say int. Now, the number of nodes in an empty tree is 0. So again, base case of 0. All right, what's my second move? Node, right? So I say node of LXR. And what this is going to be is I'm going to count all of the nodes on my left and my right, sum those up, and add 1. Okay, it's no different than what we saw before. It's similar to tree sum, except I'm not actually using this X value. So let me say count of L plus 1 plus count R. And that's the function. But here's the thing. I defined this function, but I wasn't super excited by it. I've done this a million times. Maybe you were. But the point is that this was not very fun to write. Like, I've already written a length function on lists, right? I basically just wrote another length, except for trees, where I count up basically every element in it, right? But why should I have to do this? In fact, we might duplicate our efforts a lot if we write something like tree sum, but we also write like a function to sum up all the elements in the list. That's duplication of efforts. It's duplication of code. So how can we use this idea that trees are themselves data structures that store data and kind of use like repeat usage of our previously defined list functions? And we can do that because we can try to turn a tree into a list. So what we're looking for a function f of type tree to int list. And it turns out that there's going to be a couple ways that we can achieve that. Okay, and we're going to talk about it here. Okay, so we rolled that, but it's boilerplate pretty much. Okay, so here's the kinds of traversals we're interested in. Okay, and there's going to be 3 ways that we're interested in. They're called in order, pre-order, and post-order traversal. Okay, and they're very simply described. Okay, on this next slide, I'm going to tell you exactly the philosophy that goes with each of these traversals. For in-order traversal, it's for all these traversals. Okay, you only have 3 choices. Okay, if I'm looking at a node, I'm here, and I have like a left subtree that I don't know about, like I'm holding, but I haven't looked at maybe, and I have a right subtree here. Okay, I have 3 choices. I can do my left, I can do my root, and I can do my right subtree. And when I mean do, I mean visit, right? Traverse. I'm looking for an ordering. And I can really only choose to do this, or like permute those 3 things in some way. Now, if you think about it, there's actually more than 3 possibilities, but these 3 possibilities are the only ones we care about. Okay, so these are all characterized by what their philosophy is for what that ordering is. Okay. If we start with in-order traversal, this one's the most natural, I think. It is root left right. If you can visit left, go left. And then if you can't go left, go to your root. And if you can't go to your root, well, yeah, go right. I guess you can always go to your root, but that's the idea. Okay. So for instance, if I wanted to think about how this thing shapes up, let's say I had the tree above. Okay. So it looks like this, right? I'm gonna omit the ints inside of it, right? But if I wanted to talk about how I traverse this thing, I start here at my root, and then I want to go left, and I can go left, so I do. And then I can go left, so I do. And I can't go left anymore, so I stay at my root, and I write 1. Right? But I can't go right now, so I backtrack. I go back up here, and now because I've already gone left, I visit my root, so I go 2. And then I go right because I can, so now I'm at 3. And now I can't go left, right, or root. So now I go all the way up to here. So I get 4, and then 5, and then 6, and then 7. Or actually, I think that's actually 5, 6, 7. Yeah. Basically, it reads exactly the same as if you were trying to go left to right, right? 1, 2, 3, 4, 5, 6, 7. Okay. That's the idea behind in-order traversal. And then I won't describe pre-order and post-order for you, but I'll say that they're the result of if you do root left to right and left to right root, respectively, as your philosophy of tree traversal. Okay. Okay. Hopefully that makes sense to everyone. I'm going to erase this now, and then we're going to implement one of them. So let's implement a, first off, let's implement in-order traversal, okay? So we're going to write it here. Remember, first move, empty. And I want to get out of it an int list. So I'm going to write this. All right. Now, if this doesn't make sense to you, you can think like, what's the in-order traversal of the empty tree? What is a list resulting from visiting all the elements in the empty tree? And it should be obvious to you that the answer is nil, the empty list, right? There are no elements to visit, so I return empty. Okay, fair enough. Then we go inord of node LXR, as usual, right? What do I return here? All right, so my philosophy was left root right. What that means is that I basically want to visit all of the elements in my left subtree, and then my root, and then my right. Now, what does it mean to visit all of the elements in my left subtree? That means a recursive call on my left subtree, right? If you recursively assume that inord on L will return to you a traversal of all the elements in L, then that just means inord L. That's what it is. This is an in-order traversal of the left subtree. And I want all of these before I put X and R in, okay? And then I want X, and then I want inord R, right? I said left root right. But now how do I put these values together? Well, I'm going to have to take an int and two int lists. So here's what I'm going to do. I'm going to actually, I'm going to append this, okay, to this, right? I'm going to take this int list and append it to this int list. So I'm going to have to produce an int list here. And what I'm going to do is I'm going to do this. Let's say this. Does that seem okay to you? This is actually wrong. I can't do this because this doesn't take track. X is an int here. Inord R is an int list. I can't append an int to an int list. But what's the canonical way to prepend an int to an int list? It's cons. Simply enough, right? I cons it onto the right, and then I append that. Okay. It would be, you could do this, but please don't. It's a style violation, and you shouldn't. This is not useful. This will actually degenerate directly to X cons inord R. Okay. But this is like wasted effort. You should never append a singleton list to the front. Okay. So I'm just showing you what you should not do. But we cons here, and then now we have our in-order traversal. Okay. So that's how we do inord. Right. And you can, if it's not obvious to you how it works, you can try to like kind of work through some small examples to convince yourself. But the idea is that there's very few moves we could make. There's very few possibilities that we had for what we could do here. So the fact that we did it left, root, right, and that's the specification of inord, means that like this is pretty much the only thing we could have done to make it right. Okay, that's not a super strong justification, but we're not going to prove it right now. Okay, and I'm going to write preord, which is subject tree, return set int list. I'm running out of room, so I'm going to put equals here. So we're going to write preord now, but now I'm going to tell you that we're doing preord traversal, so now we're going to do root left right. Okay, I'm going to splay it out along two lines, but I already did the empty case for you. If it's empty, then we're just going to have the empty list, right? Because there's nothing in the tree. But if I preord of node LXR as usual, well, now what do? I have to do root, then left, then right. So what it looks like is I'm going to do something like this. X, I'm going to call myself recursively on the left, and I'm going to call myself recursively on the right. And now how do I stitch this up into a valid int list? I'm going to take these two int lists and append them together. And now I have an int with an int list, so I'm going to cons it on. That's all. That's all you need to do. So with this, now we have our implementations for in-order traversal and pre-order traversal. Very short, very concise, very simple, right? It's very terse how you can define this in SML, but that's the power of recursion. Because someone invented a technique for cognizing literally infinitely many facts in your brain. And by the way, it's called recursion or induction, depending on how you look at it. Okay, so this is a demonstration of how we can do recursion on trees. And now, if I have inord, I could do something like this. Instead of using count, I can say length of inord of t for some tree t. Okay, And I'm going to tell you that this should be essentially equivalent. I'm going to run out of room here a little bit. But this should be essentially equivalent to count of t. Okay? That's our idea. That's why we defined inord. Okay? All right. But now we wouldn't have had to write count if we wanted to. All right. Okay. And I already showed you this. Cool. Quiz time. I'm going to drink some water and take a break. Okay. Let's get back to it. So right now we're going to do a structural induction proof on trees, and we're going to prove an equivalence, sort of like the one I was talking about with count and length. But we're going to show that doing that tree sum function I was talking about earlier and doing a list sum instead on the in-order traversal of that tree end up with the same thing. In a sense, we're showing that the data is preserved. Okay, we're going to prove that inductively. How? Structural induction. Okay, so I've already talked a little bit about structural induction, but we're going to be able to do it on trees. Why? Because trees are built up from other trees in the same way that lists are built from other lists, in the same way that natural numbers are built from natural numbers. Anytime you have that kind of hierarchical structure, an inductive definition, we call it, you have induction. Okay, so this is the principle of structural induction on trees, and it should be very familiar. So if I've got a theorem on values of type tree, I want to show that for all values that my property holds, I need to show only two things. I show that P of empty is true. I show that assuming that I get both P of L and P of R, that is that P holds for some arbitrary L and R values. Okay, if I have that, then I just need to show that P of node LXR holds for an arbitrary X. And this should look familiar, but also not, because before we just had one induction hypothesis, right? But now we get two. Why? Because I have two trees on my left and right that I need to be able to say the theorem holds for. If I don't know that the theorem holds for my left and right subtrees, I'm up the creek without a paddle. I don't know what to do. My moves I can make are very limited. But I need that principle of induction to be able to talk about any of my children. Okay? So for a tree, I get two, all right, for an arbitrary L and R. But you have to say for like some L and R. It's still not proper to say for all T of type tree. Okay, that would still be assuming the theorem, but you just get two, all right? No more, no less, right? Well, actually, I guess you don't always need both your induction hypotheses, but for the vast majority of functions you could write on trees, you will need two induction hypotheses. Okay, and I already wrote all of this on the board, but you can take a look at it for a second. So we have in-order traversal that I already wrote for you earlier. We have a tree sum function and we have a list sum function. And I'm going to tell you that we're trying to show that they do the same thing, even through the conversion of inord. Okay, and that's the theorem in particular, right? So let's get to the proof. And I've got two lemmas for you. Actually, I'm going to hide that one because I don't want you to look at it. Okay, and this is one of our lemmas, which is that a list sum of L1 append L2 is the same as summing the list sum of L1 and L2 separately. All right, cool. So let's use proof. The first thing I got to do is write what kind of induction I'm doing. So we proceed by structural induction, right? On what? On T, which is of type tree, but we can just say on T. All right. If I want to prove something about every possible value, I can do it by induction or I can do it by letting it be free. Here I have to be able to decompose on the structure though, so I want to do induction. All right. So if I proceed by structural induction on T, the base case for T is when T is equal to empty. Our technique for how we're going to do these proofs is we're going to try and start at the left-hand side. Okay, so like when I say left-hand side, I mean in an equivalence proof, I have a left-hand side here, which is tree sum of T and list sum of inord T. In fact, let me write that down explicitly. This is my LHS and this is my RHS, right? Left-hand side and right-hand side. And what I want to do in this proof is I want to take the LHS and I want to like step it to something. I want to show that it's extensionally equivalent to something, and then eventually arrive that it's extensionally equivalent to like E. And then I'm going to get stuck. I'm not going to know how to proceed. I'm not going to know what move to make. That's okay, because what I'm going to do is then I'll start from the right-hand side. And then I'm going to simplify it. I'm going to show that it's equivalent to something. And eventually I'm going to try and show that it's equivalent to E. So I'm trying to have them meet in the middle. I told you earlier that extensional equivalence is an equivalence relation. That means it goes both ways. So if I show that LHS is equivalent to something and RHS is equivalent to something, I have shown that LHS and RHS are equivalent. Okay. The reason why it might seem like it doesn't matter the way we do it, and in a sense you're right. This will make citing justifications a little easier for us. Okay, it'll make it a little easier if we don't do something called backward stepping, right? Cool. Let's say I don't need this. Okay, so let's proceed with the proof. Well, let's start with the LHS, which is tree sum of T. So tree sum of empty. And we know, and remember that the way that we do an induction hypothesis is we have a knowledge bank, and this is our knowledge bank. This is everything we know about the world, okay? Plus or minus a few other things we know about, okay? But basically, if you're ever looking for something to do, it's up here. This is the list of possible moves you can make. It's like chess. I've laid out everything that we can possibly say, and we have an equation here. I'll say equation for like an equivalence, right? Between tree sum of empty and 0. So what do I say? I say equivalent to 0. And then I give justification. Why? By clause 1 of tree sum. All right. And now 0 is pretty much as simple as it's going to get, right? So let's say that we're stuck. All right. Let's say we're stuck, and let's say that, let's call it for the LHS. Let's do it from the RHS now. Well, if I have list sum, remember the RHS is that quantity up there. If I have list sum of inord of empty, I'm going to do two things. First off, I want to be able to set this. But how do I simplify list sum? Well, I only have an equation for when list sum is taking in nil or x cons x's. Inord of empty is neither of those things. I don't know what it is necessarily. I have to do eager evaluation. I have to swap it for something by SML's evaluation rules, because I want to use the definition of list sum, but I can't yet. Okay, so I'm trying to get at that by using inord. So what does the definition of inord say? Well, I have an equation that says inord of empty is nil. So let's use that. So this is equivalent to list sum of nil, right? And that's by clause 1 inord. Okay. Clause 1 of inord. And then I have list sum of nil. So now I know that's got to be 0 because I look up at my knowledge bank and I find it inside. Okay. Very, very procedural. That's 0. So I say clause 1 of list sum. And now I've set LHS, or I haven't set, but I've shown it's equivalent to 0. And I've shown the RHS is equivalent to 0. Therefore, they're both equivalent. And that's the base case is done. Okay. Little check mark. But we're not done yet. Okay, we have more stuff to go. So let's see. Let me think about this. I'm going to write the induction hypotheses on this board, and then hopefully we can just remember it when it comes later. Okay. So this is the base case done. Remember, we get 2 induction hypotheses. So what are they? Well, I'm going to say IH1. We assume the theorem, but for a specific L. So for some, I'll say for some L of type tree, we get that tree sum of L, sum capital, is essentially equivalent to list sum of inord of L. Okay, that's my IH1 for some L, a specific L, a fixed L. What about IH2? Well, where do you think IH2 is going to look different? It's going to look different in exactly 3 places, which are everywhere I mentioned L. So I'm just going to do this. Okay, I'm just going to write equals R equals. It's going to be exactly the same, and I don't want to write it all out again. So it's the same sort of deal. Okay, that's our IH1 and IH2. Okay, all right. I'm going to put this away now, and we'll go work on the inductive set. All right. And we will refer back to this in a second. Okay. All right. Inductive step. With our L and our R that we received from the induction hypothesis, we want to show, so WTS want to show that tree sum of node of LXR is equivalent to list sum of inord of node of LXR. And I caution you to please write this out specifically. Write out what you want to show. It will help you. Okay? Because now this is our new LHS, and this is our new RHS, okay? And we're trying to show that these two things are equivalent, okay? I hope I have enough room for this. Let's try it out, okay? So let's start from the LHS, right? It's tree sum of what I just said. Okay, so here we want to be able to apply our definition, and in fact, do we have an equivalence that says something about this? Turns out we do. Why? Because tree sum of node of LXR is just tree sum of L plus X plus tree sum of R, okay? So by unpacking the definition, I'm going to say this is equivalent to, I'm going to put it on this new line because I'm going to run out of space, I think, otherwise. Is equivalent to tree sum of L plus X plus tree sum R, okay? And that's by clause 2 tree sum. Okay. I'm trying to leave like half this board empty, hopefully. And I'm also going to notate this is LHS. Okay. All right. But now what do I want to do? I want to be able to say something about tree sum of L and tree sum of R. Now, we do have two induction hypotheses that could help us with that because we know something about tree sum of L and tree sum of R. So let's actually do that. Let's say it's so we're going to call IH and say that we're at inord of L, right? And sorry, not inord of L. List sum inord L plus X. Yeah, okay. Plus list sum. I'm going to break it apart here, and you'll see why this is in a second. List sum inord of R. Okay. So this is what I step it to because I apply the induction hypothesis on both of these guys, and I get these. Okay. So I'm going to say by IH times 2. Okay. But now I want to say something about inord of L and list sum of that. But do I have anything that says anything about inord of L, like for a specific L that I don't know? I don't. So what I need to do is give up and go home because I don't know what to do now. So I'm going to give up and I'm going to go to the right-hand side. And it's okay to give up. This is a life lesson. All right. Let's start from the right-hand side, which is this guy. So if I have list sum inord node of LXR, I want to step this. What do? First thing I do is I look at the definition of list sum. Can I apply list sum? Do I have anything that says what list sum of inord of node is? I do not. I only know a list sum of nil x cons x's, and in this case, append of two things, okay, because of our lemma. So I can't do anything here, but I can simplify inord, because what do? I know that inord of node of LXR is this. So I'm going to do that. So I say equivalent to, I'm trying to walk you through like my whole like proof writing process, right? This is exactly what I'm thinking when I'm writing the proof. It's a very formulaic way of doing it. Inord of L, append x cons onto inord of R. I'm going to write in here like margins in small, clause 2 inord, okay? That's our justification. Okay. But now I'm in a pickle, okay? Because what do I have? I have list sum of inord L, append quantity x cons inord R. But list sum only applies to these two things. Oh, wait, we have a lemma for that. Except we don't. This is going to be very subtle, but it will not be correct for you to step this. So actually, let's write it out. So here's what we want. We want to be able to say, oh, I have list sum of L1 append L2, and I know that's equivalent to list sum of L1 append plus list sum L2. So this looks like L1, right? And this looks like L2. So I want to be able to use that to say this is equivalent to list sum of inord L plus list sum of x cons onto inord R. Why? Because I'm using L1 and L2 as stand-ins for these two, right? They look the same. And what I want to be able to do is I want to cite lemma 1. But I'm going to tell you right now, this is wrong. This will get you points stocked off. You can't do this. The reason why you can't do this is because you need more justification here. Why? Because look at our lemma. It says for all values L1 and L2 of type int list. Is inord L and x cons inord R Are those two technically values? Are they valuable is a bigger question, okay? I don't really care so much if they're values, so much as if they are valuable expressions. Because so long as they're valuable, I can swap them for their values. That's what referential transparency says, right? But I want to say for all values. So I have to show that in order L and xcons in order R evaluate to values, that they are valuable. Now you might look at the definition of inord and say, oh, inord is total, right? So it must be valuable. But you need to show that to me. I need you to cite that to me. So here's what I'm going to do. I'm going to activate my computer again, even though I won't need it for right now. Here's what I'm going to do. I'm going to reveal to you what our hidden lemma was the whole time. So I need to show the value. Okay, actually, let me hammer this in a bit more. I need to show that this is valuable, this yellow thing, and this. Wouldn't it be great if I knew that inord was total? You can't cite that without proof. If you want to prove or cite totality on an assignment, either you will have it as a lemma or you'll have to prove it on the spot. In this case, the lemma I was hiding from you was the fact that we were given, while we were doing this proof, the fact that inord is total. That was the secret. So we can cite it. But if you don't have that, you'll have to prove it, okay? But note that this begins a chapter in your life called totality citations, where you have to write that things are total on certain lines to be able to make a step go through, okay? And what I'm trying to get at is to show you that this step is based on whether or not you need that a particular expression is valuable, okay? The way it goes, and let me actually show you this because I have slides for this explicitly. I've already talked through all this, but this is what I call stepping through theorem values. If you want to step through a theorem or a lemma that has a value in it, something quantified over values, you have to show that whatever takes the place of these variables, like L1 is, inord of L, you have to show that that thing is valuable. And how do we do that? We're going to be able to use totality as a tool to get at valuability. We want totality for the purpose at getting at valuability. That is the important thing, okay? So here's the picture, okay? I want to use a theorem which relies on E being valuable. So I want valuability of E. And I want valuability of E, so what do? I can get it via a totality citation, usually. If this was if this was list sum of nil, I would have no problem with you not citing totality here to step, or if both of these were nil, okay? But they're not. They're expressions in the form F applied to something, which means they could loop, they could raise an exception, which means that they might not be values, which means this theorem might not apply. If they were nil, that would be okay. But because they're function applications, we have to be careful, okay? So to repeat it one more time, we want valuability, we get it via totality. So what I'm going to do is I'm going to erase that here, and I'm going to say to make this step, we have to cite also lemma 2. Because we want to show that inord of L and xcons inord R are valuable. Now you might also be wondering, I showed that inord R is valuable. How do I show that xcons that is valuable? The reason is because cons is a constructor. Constructors are always total, okay? You don't have to cite that. You don't have to cite that constructors are always total. But just know that, and that's important, okay? So because this is valuable, and this is a value, right? Because x is a value from the node, and this is valuable, by the definition of totality, this must also be valuable. So we're done. So now we can make this step. And now it almost looks like what we want, right? We want list sum inord R, L plus x plus list sum inord R, not list sum inord L plus list sum of xcons inord R. But handily, we can step through the definition because what do we have? We have something which talks about, here, list sum of xcons x's, okay? So let's step it. So I'm going to leave this left-hand side list sum alone. I'm going to just call it inord R, or inord L. I'm leaving this alone, but I'm going to say plus, and I'm going to break apart this definition to x plus list sum of inord of R. And can I just say clause 2 of list sum here? The answer is no. When I say stepping through theorem values, I mean also definitions. Why? Because definitions only apply to values. Remember, eager evaluation. I only can step this xcons x's if x is a value and x is also a value. So if x is not a value, I can't do that. So basically, concretely, to set x cons in order r, I have to know in order of r matches to x's, which means I have to know it's a value. So what do? I cite totality again because I need in order of r to be valuable. So I do lemma 2, and I know this is like getting a little hard to see, but we're fitting it on a board at any rate. Okay, so okay, so that's our proof. That concludes it because now look at my left hand side and look at my right hand side. They look the same. And if you're confused over the formatting, it's should have done that earlier. Okay, that's the proof. 2 totality citations, but be aware of where you need to do them. All right, valuability. All right, we'll stop talking about it. I just wanted to say this again because this will be on your homework. All right, this is something you will be tested on. All right, and then we finish off our proof and we're done. Actually, this one I did the induction hypothesis on the right hand side. It doesn't actually matter, but yeah. So now by the principle of structural induction on trees, we've proven our theorem. That's it. We're done. Okay, that's the proof. All right. Okay. We're going to move on. We're going to talk about data types now. You can look back over the notes to look at this proof, but this is one of the most involved proofs we're going to do all year. Okay. So I would just try to be aware of what exactly happened, and more than that, be aware of the process. Right. I try to be very transparent with my thought process while I was doing that proof. Okay. I'm trying to show you how to think when you do the proof. When you're stuck, give up. And when you don't know what to do, consult your knowledge bank, which I just erased. Consult your bank of facts that you know. There's only a finite amount of them. Okay. We're not going to give you infinitely many. Okay. I don't think I need too many boards for this. I'm going to just move on. Okay. We've seen trees. Let's go to lists. So suppose I wanted to write this function here. It's called last. I take in an int list and I give you the last element in the list, kind of the opposite of the head function I showed you earlier. And we can try to write it, but I'm going to tell you that right now, we already get into an issue right off the bat. Why? Because we don't know how to write the base case. And I'll write this out with you. So last, and I want to take in an int list and then give you back an int, right? But what do I return in the base case? Well, I don't have a last element, right? So what we could do is we could raise an exception. Okay, we could like not handle it and then force handlers of this function to deal with it. That's kind of gross. I said something earlier about how exceptions, when you have exceptions, it's like they percolate up and then they disrupt your entire execution, and now your machine is just crashed. Your process has crashed. You're just like done completely. So if I raise an exception with last, if I've got someone over here trying to write like val x equals last of nil, this will raise an exception on them, and they have no choice but to deal with it because they don't have a way of handling this, at least not yet. Okay, so what we're going to find is that we don't want to be able to raise an exception, and in general, functions that raise exceptions are really bad. Okay, so here's what we're going to do. Okay. I should also say the alternative here is also we can return like 0. We could just return like an arbitrary integer, maybe -1. I don't know. But now you've made ambiguity because this is ambiguous with the case where, and let me finish writing last for you actually. So if we wrote that we return -1, well, I also want that last of the singleton list is going to be that element. And then last of x cons x's is last of x's, right? I'm going to recurse on the rest of my list because I don't care about the first element. But now there's ambiguity between if the list is empty and if the list was the singleton of -1. Basically, I'm showing you that last of nil is essentially equivalent to last of singleton list of -1. This is ambiguous. A person using this function doesn't know which case they're in. So let's not do it. Okay. We want to distinguish found 0 or found -1 and found nothing. All right. So this happens a lot actually, where we write functions where some inputs don't have a good answer for you. Okay. And what we've done so far is in the case of div, we raised exceptions. In the case of fact, we've infinitely looped. But neither of those two things are desirable because a person calling that function has no way to deal with either an exception or an infinite loop. What are they going to do? They have no agency. We want to give people using our libraries some agency, okay? Even if they break our preconditions, okay? Because they might make a mistake when they do it, okay? So we're going to declare a new data type called option. And here's how I'm going to define it for you, okay? I'm going to say that data type int underscore option. I'm doing the underscore for syntactic reasons. Don't think too hard about it. Okay, just think about the content, right? Basically, it's because I'm lying to you, and there's a extra language feature I'm going to show you in 2 weeks or 1 week where this will make sense. All right, so an int option has two constructors. It's either none or it's sum of int. Okay, an int option is one of two things. It is either no data. None has no interesting data in it whatsoever. It's just none. It's nullery. It's a nonsense output. Okay, but it's a value at the very least. Or it's sum of an int. So either we have an int or we don't is the idea of an int option. Okay, and you don't know which one based on the type. If I hand you L of type int option, you don't know which one you're holding, but you know that it might be a mistake. This is the type. Options are the types of fallible data. Okay. And what we find is actually it's a type constructor, which is to say that int options are not the only options that exist. We also have string option, and we have int list option, and we have int option, so on and so forth. Okay. Okay. So for any type T, we have type T option. And I already showed you the constructors. And yes, none is a constant constructor, but I want to show you some examples. So if I have sum of 5, so sum applied to 5, sum is a function of type T to T option. It's of type int option. If I have sum of a list, that could be of type int list option. If I have none, it could be of type int option. And if I have none, it also could be of type bool option. None could be of type any T option, right? Because it's ambiguous which one it is. So these are examples of options. But we can use this option idea to help us rewrite last. So what if instead of returning -1 as like a dummy value, right? Because it's ambiguous, we separated it by returning not an int option, non-int, but an int option. And int option is with no underscore. Okay, this underscore, don't worry about it. All right. So int option equals none. I have no last element. Last might return no data. So we return none because there is no last element. Otherwise, instead of x, we return sum of x. And otherwise, our code remains the same. It looks very much the same, but now a user of last, this is no longer true, right? Because this will now evaluate to none. So let me break this equivalence. And this will evaluate to sum of -1. This equivalence is no longer true. And what does this look like for a person calling our function? Well, I'm going to erase this actually. If a person was calling last, before they might say something like last of x's. And this will just raise an exception or loop forever. But now they have the option to say this. Case last of x's of, and there's two cases. The none case where they get to do something, or the sum of x case where they now have an int called x and they do something. But now there are two cases, two branches for this function. Okay. Now I have agency. Now I can use this function however I like. That's the power of options. Okay. So anyways, to move on, these things are called variant types. Okay. They're constructors that have variants that they can be. And this is important to realize because variant types, we've already seen actually. You can think of lists. Lists are also a variant type, right? Because lists can be one of two things, which are they can be nil or they can be cons. Trees are variant types. They can be either empty or node. And honestly, you can think of integers also as variant types because they can be 1 or 2 or 3 or -1. It's just that ints are infinite. Okay. Okay. But the real power of variant types is that we can case on each of the cases, each of the variants it can be. It's also called a sum type, which is a little easier. Okay, say. So you can think of the definition of int list this way. Okay, it's nil or it's cons of blah blah blah, where cons is also infix. Okay, so that's one way you can think about it. Okay, but this is the definition I gave on the board earlier. Okay, We also call these algebraic data types, and later on I will try to show you why it is that algebraic data types are very, very cool, right? But let me just context switch entirely. We're going to talk about something completely different. All right. I am interested in this problem. And, somewhat surprisingly, you're going to find that this problem is actually related to what we're talking about. I'm interested in a comparison function on integers. That is, it's a function that takes in two integers and outputs whether or not what their relationship is with each other. That is like, CMP of x, y, x could be less than y, x could be equal to y, or x could be greater than y. In most computers, or not in most computers, but most programming languages that don't have these algebraic data types, here's what they do. They say this is equivalent to, this goes to int. Why? Because they say like CMP of 1, 2 goes to -1 because 1 is less than 2. And they say that CMP of 2, 2 goes to 0 because they're equal. And they say that CMP of 2, 1 goes to +1 because 2 is greater than 1. But now what does this look like for a consumer of this data? If I want to use CMP, right, I might write this. Case CMP, and I don't know what x and y are, so let's say an arbitrary x and y, of, well, I know there's a case where it's -1, so I can pattern match on that. I know there's a case where there's 0, so I can pattern match on that. And I know there's a case for 1, so we can put whatever here. But actually, let's even do it. Let's put this into the playground. So vim test.sml. Let's say that we have, yeah, let's just do it. Okay, so xy, if x is less than y, then -1, else if x equals y, then 0. And then else we're going to return 1, right? Those are our three cases. And I'm also going to annotate this. Our type int, this is of type int, and this is of type int, okay? What if I had a function like foo, which takes in x of type int and the y of type int? And here's what it wants to do. Case CMP x, y of, let's say 0 goes to, or -1 goes to the string L, and then 0 goes to the string E for equals, and then 1 goes to the string G for greater. Let's type this into SMLNJ and see what it says. Warning, match non-exhaustive, right? Why? Because I wrote this comparison, I wrote this pattern matching, but if you see here, I didn't handle every possible case. There are more cases than the ones I've written on the board. There are more cases than 0, 1, and -1. I've lost my chalk. Here it is. There are more cases than these three. I have to add a wildcard case or the compiler is going to yell at me. And this is a style error. But this feels really bad because I know this case is impossible. I know by post-condition of CMP that it should never return something that's not 1, 0, or -1. But it does so anyways. I have to explicitly handle it. That sucks. How can we do better? All right. I'm going to show you a first cut at this, and then we're going to improve on that. All right. So let's suppose that we use what's called a type alias. All right. I'm going to write it here. So type order equals string. Okay. This is called a type alias. I'm saying that the type order is a new type that is literally just the type string by a different name. Okay. So our first cut for the type order will be string. So our comparison function will return the string less if it's less. It will return the string equal if it's equal, and it'll return the string greater if it's greater. Okay, that's our first cut. All right, that's all it does. Well, what does it look like for a consumer of this data now? It looks like this. Case compare x, y of, and now I handle the string less, I handle the string equal, and I handle the string greater, but it's still possible for me to mess up because there's another non-exhaustive check here. I have to add an explicit case for all the strings I didn't handle. So it's the same. I haven't improved my situation. I'm in the same situation, but now there's infinitely many strings as opposed to infinitely many ints that I'm not handling, right? So this shouldn't be possible. And actually, there's a second issue with what I have here. The second issue is that this code plain doesn't work. I said that compare returns less, equal, and greater undercase, lowercase, which is different than uppercase less, equal, and greater, which I'm casing on here. So if this was our code, if this was our comparison function, actually every output would go into this wildcard case that we said shouldn't be possible. And this happens all the time. People say, oh man, this is impossible. This shouldn't be possible. Let me raise an exception. Okay, I reasoned about it and this shouldn't be possible at all. But guess what? Even the most seasoned of engineers make that mistake all the time. They say, oh, this is impossible. And then guess what? It was possible the whole time. It's kind of a motivational story. So, but in this case, not so motivational because we don't want it to happen. So let's exclude the possibility of making this mistake. Let's try to make it so that in a type safe way, this can never happen. Here's how we're going to do it. We're going to define. So instead of, okay, CMP insert int goes to order. All right. And then this is no longer going to be true. But we're going to define a new type for order. Okay. And I'm going to keep this around here because we're going to look at how we use the type. So I'm going to say data type order. I'm going to define a new data type. And what it is it's three things. I'm going to put it on a new line, but it doesn't matter where you put it. It's less or it's equal or it's greater. The order type has three constant constructors. It is either less, equal, or greater, and nothing else. It's just a flag that has three different states it can be in. And that's going to be what we want to return here. So to implement it, well, I guess I have it on this next slide. But actually maybe this is just some kind of like motivational stuff I wanted to talk about. I wanted to just say we're trying to find the best solution, right? Like the int solution works, but it's not the best solution. So let's find the best one. All right. So with data type order equals less, equal, or greater, this is our new comparison function. If x is less than y, we return an order, which can be only one of three things. So we return the constant constructor less, which is a value of type order. Otherwise, if it's equal, we return the equal constructor. Otherwise, we return the greater constructor. Okay. And now if I'm using this code, what am I going to write? This is like separate. Don't worry about it. Case CMP of, what am I going to case? And I realize that's called compare and that's called CMP. Realize I meant the same thing. Okay. I only have three cases now. I have the less case. I have the equal case. And I have the greater case. And the great thing about this is that the compiler is not going to yell at me. I have no other cases. This is it. This and nothing else. That's the idea of sum types. This and nothing else. Less, equal, or greater, and nothing more. No fat. Okay? We're going to be able to write really clean code that handles every case and never be assured that we can never reach a case that we thought was impossible. That's the strength of algebraic data types. Okay. Okay. Oops. Okay. So this is the code that we write. Again, if we had misspelled one of the strings that we had back when we returned strings as our order type, like that could have gone into production. That could have gone anywhere, and we wouldn't have known because we made a typo. It's impossible to make a typo here because if you write like equa, the compiler will be like, I don't know what this is. What is this? This is not a value of type order. Equa is not a value of type order. So therefore, let me not even accept your program. One interpretation, one canonical way to do it. That's the idea. All right. Types guide structure. We structure our types to fit our problem, to frame our problem. Okay. Our way of thinking is through our types first. Okay. And let me actually just briefly demonstrate to you what it does. So if I say data type order equals less or equal or greater, and this comparison function now returns less, equal, and then greater. Well, okay. I'm just going to show you the Let's just say everything goes to 0. I don't really care. Actually, no. I'll make it different. Greater. Wait, I put in a string. Sorry. Yeah. Okay. Here we go. No comments or no quotes. All right. Now we want to do this, and then CMP returns an order instead of an int, right? And this does compile. And better, I'll show you again, if I make a typo, I write equa, SML will be like, wait, match redundant. I don't know what you're talking about because equa is now a variable name, but it will warn you is the idea. Okay. You can still fall prey to this if you ignore the match redundant, but be careful about it. Okay. So this is way more resilient. It's way more resilient. Cool. I was a little wrong when I said it wouldn't know what it was. It'll actually match to a variable case, but that's a different story. Okay. All right. I have a little bit of time to talk about this. To talk about this last thing with you. Whoa. Okay, that was weird. All right. Cool. All right. This last thing I want to talk about is called typecasting. In other programming languages, there's an idea of typecasting, which means turning like a value of a type into a value of another type for free. That's not what I'm talking about. I'm talking about typecasting as in something else. I'm making a joke. It's kind of a pun. All right. I'll reveal to you what I mean at the end of this lecture. All right. But SML does not have typecasting in that sense, but it does have typecasting in this sense I'm going to talk about today. All right. So the idea is that when we're solving shapes and sizes, like there's so many different kinds of problems that have kind of common roots. You know, there's a lot of problems. Whoa. Yeah, I think I got it. It's just like a. Oh, here we go. I don't know how long that's been there for, but okay, whatever. Yes. I said something about how like lists and trees are like common ways to solve problems, but they come in all shapes and sizes at the end of the day. But the great idea behind algebraic data types is make your types fit your problem. Make the types serve you. Okay. And here's our problem. Okay. We have a class of people. All right. Some people are employed, some people are students, and some people are unemployed. It happens to be that we live in a world where those three things are not disjoint. But in this problem, let's assume that all three cases are disjoint. Okay. You cannot be both a student and employed or a student and unemployed. Okay. That's the idea. All right. This is our problem. And suppose that we're interested in just a few things. All right. For all these people, we're interested in their name. We're interested in their paycheck if they're employed and their tuition if they're a student. We're interested in the company that they work for if they're employed. We're interested in the number of courses they're taking if they're a student. And if they're unemployed, if they were ever employed, we're interested in two things, which are the days since their last employment and the title of their last job. And again, this is only if they were ever employed. Some unemployed people have never been employed. Okay. And those are all the things we're interested in. And we can try to represent this in a way using SML. Okay. What we're going to do is we're going to use a big tuple and we're going to use the options that we just learned about because, you know, if we don't all want to store like the name of or the paycheck of a person that's unemployed, or we don't want to store like the company a person works for if they're a student. So we're going to have an option. So we have the option of having none if that's the case. And this is the type representation. Okay. We have a data type class, which is employed or student or unemployed. So this is like three things. It's kind of like order. Right? It's just telling us what we're in. And this is our type. It's a type alias. And I know it looks scary, but this is just a tuple type. Ignore the comments. It's a tuple of 6 things. One is a string. One is a real. One is a string option. 2 of them are int options, so on and so forth. And what they mean is in the comments here. So the string is their name. That always exists. Okay. The real is positive if they're employed. That's their paycheck. And if they're unemployed, it's negative and it's their tuition. Or rather, if they're a student. If they're unemployed, it's 0. This string option is the company name if they're employed. Otherwise, it'll be none. And this int option is the number of courses they're taking if they're a student. Otherwise, none. Okay, so like let me actually copy this down for you here. I don't remember whether or not I have a file with this open, but that's fine. Yeah, okay. So this is good enough. Well, okay. Sorry, let me adjust this right now to make this valid decimal syntax. The comments got messed up, but don't worry about it. Actually, maybe do worry about it. You know, let's just run with it. Okay. So this is the idea. And I'm going to make a value, P of type person info. Okay. And it's going to be like their name is Bob. They're employed. So the paycheck is 2000. I don't know, like 2000.0. Maybe they make it like very little. And then this was supposed to be the company name, number of courses, and then days since last employment. Okay. Now, Bob is employed because they have a positive paycheck, right? So we're also going to say that Bob's company name is, let's say, I don't know, maybe they work for Bank of America. And then the number of courses they're taking is none because they're not a student. The days since last employment is none because they're employed. And the last job, if unemployed, is none because they're not unemployed. So Bob is employed. We might also have another person. Let's call this person Anne. And Anne is a student, so their tuition is negative negative $50,000. Okay, and it's a real. And then their company name is going to be, oh, so this is some, sorry. It's some Bank of America because Anne is a student, so she doesn't work for a company. And the number of courses she's taking is sum of 5, but she's not unemployed, so the last two are none. Okay, and if we run through this through SML, this should type check. Great. So we're convinced this works. But look at what I had to do. Look at the hoops I had to jump through to make this work. I had to put none in like 3 different places to make this work. Like it's disgusting, and I have a bunch of floating invariants because I have to make sure that if your real here is positive, then these 3 should be none, and if you're a student, then these 3 should be none. If your tuition is negative, but also this should be set. There's so many invariants. Okay. Again, remember what I said about invariants. You're going to get it wrong. You're going to mess yourself up. So let's try to do, and also, let's say that also a person is equal to a tuple. So we also said data type class equals employed or unemployed or student. So a person is going to be a tuple of 2 things, their class and their person info. So if I want to say I had a person, I would put it in a tuple where the first thing will be Bob is employed and then Anne is a student. And this should type check as a person. Oh, whoops. Sorry, here. Okay, this should now, whoops, I put a, all right, this should now type check. So I have 2 people, but another thing I can mess up is this tag here, this employed, needs to make sure that this real is positive. There's another area of mismatch. Via just the type, we have so many points of error, okay? How do we do it better? Let's try doing it better. Here's my other motivating thing to you, which is like, if I wanted to write a function that took in a person info and raised the tuition by 4%, if you apply this to an employed person, this will give them a 4% raise. If you apply to an unemployed person, the real that's stored with them is 0, so it won't do anything. But the idea is like, we can write code that applies in cases we didn't want it to, because it's too general, because the types are too general. Let's make it specific, okay? So here's what we're going to do better. This will be our new type. Now, instead of having employed and student and unemployed be unaffiliated tags, we're going to put the relevant data with the constructor. So employed is a constructor that takes in 2 things, a real and a string. It takes in the paycheck and the company name, because those are the only fields that matter to someone that's employed. To a student, it takes in a real and an int tuple, because the only 2 things that matter to a student are the real, which is their tuition, and the number of courses they're taking. If they're unemployed, there's only 2 things that matter, but it's an int star string tuple option. What this means is that unemployed takes in either none, or it takes in some, where that sum is a tuple of int star string. Basically, it means that the int and the string they have to both exist if any of them exist, okay? And the reason is because if we're talking about the days since last employment and the name of their last employer, one of these, you shouldn't have days since last employment, but not have a name of your last employer, okay? It's either you were never employed or you were employed and you have both of those data, okay? So this is our new type. And I actually miswrote this. This is supposed to be data type, but this is the idea. And we also factored out type person equals string star that, a tuple of the string, because every person has a name, okay? Note also how unemployed people don't have a real, because they don't have a useless 0 real, okay? Because they don't have a paycheck. So let's take this and put it into SMLNJ. We're going to put it directly into the file that we were working in. Okay, let's do it. And this is going to be indented weirdly, but I'm going to fix it, so don't worry about it. Okay, and this is actually data type. Okay, and this should now look familiar to everyone. Okay, cool. So this is how we used to declare a person. Let's do it differently. Let's do Bob again, but now as a person with this new representation. And essentially, I've like shadowed the type here. Essentially I've shadowed the type. So don't worry about it. You can do that. Okay. So if we want to define Bob, and let's not write P, let's write Bob. So let's say val Bob is going to be equal to this. All right, it's a string, it's a tuple of a string star class. So his name is Bob and his class is employed. But employed only takes in 2 pieces of data, his paycheck and his company name. What did we say it was? We said that his paycheck was $2,000 because he's getting cheated by his boss. And his employer is Bank of America. No options necessary because we have all the data that we need. No nuns, no options anywhere. And now if we wanted to define Anne, we can say that Anne is a person whose name is Anne. She is a student and her tuition is negative $70,000. Sorry, $50,000. And then her number of courses she's taking is 5. Again, real string, no options because we isolated it to the case that we care about. And now if we run this through SML, it works. It compiles. And it's way better than what we had up here, where we had like 3 different nuns or 3 different nuns. And this is actually what other languages kind of do. You might have like a bunch of fields where all of them are called nullable, and then you set them to like null or none, and you have to just deal with that. And you might mess it up. You might make it something that's not none, not null, but that's on you. That's now your prerogative. So don't do that. What I'm trying to show you here is that the power of types is that we can craft types to fit our problems such that we don't need unnecessary representation. The official mantra is make illegal states unrepresentable. If a state shouldn't happen, make it so that you can't possibly phrase it, that the program will complain at you before you even get the chance. That's the idea behind types. So to finish this off, I'm going to talk about this idea I call typecasting. So again, it doesn't mean turning a value of a type into a different type, but it's just like something I made up. So don't say it to anyone else. It all makes sense to them. Similarly to how we have blacksmiths, okay? And you have a blacksmith and they have like a mold and they cast metal by like pouring metal into the mold to make like a hammer. And depending on what the mold is, they get whatever they wanted, right? They cast metal to fit whatever tool they want. Typecasting is my tongue-in-cheek way of referring to this phenomenon where you fit the type to your problem. You cast the type into a mold that fits whatever representation you want because you have that power. That's what algebraic data types let you do. And that's so different than many other languages, honestly. Some languages don't have this. I'll leave you with this final note that an imperative programmer tries to fit square pegs into round holes, but a functional programmer sees a hole and can make a peg to fit it. Any hole, every hole, right? Thank you.